This one looked kind of interesting. This one's from India. So we have triangle ABC is an acute triangle with altitude AK. All right. H is the orthocenter. So let's draw another perpendicular. Why not draw all three? O is the circumcenter. Okay. Suppose KOH. Okay, so let's rename this H. Cut off some of the excess. Okay, so we need KOH to be acute. So I'm gonna have to move the figure a little bit. That looks kind of acute. I want it to look isosceles, but okay. P is the circumcenter of KOH. All right. So we'll call it P. And Q is a reflection of P over HO. And we want to show Q lies on the segment joining the midpoints of AB and AC. Okay. All right, seems interesting. I don't want to make it look like Q lies on the circle, so I'll do something like that. Okay. So Q is a reflection of P over HO. So HO is the Euler line. So that means if we drew PQ, it would meet segment HO at the 9-point center of the circle, which is very interesting. So I wonder if we can, basically we want to show, we need to show if you reflect P over the 9-point center, then it lies on FG. So, okay, so let's draw the 9-point circle. Those look kind of tangent, actually. Oh no, those circles aren't necessarily tangent. It just looks that way. Okay, so we have this 9-point circle through all these different points. And we want to show that Q lies on FG, which is a chord of the circle. Another way to say that is the height, the perpendicular from Q to BC is half of AK. That's another way to say it. I wonder. Thinking how to do this. So how do we use that P as the circumcenter of HOK? We use that P is on the perpendicular bisector of OH. We need to use another fact about P. You could use that it's on the perpendicular bisector of HK. I feel like that would be helpful. So I think I have an idea. Basically, we want to show that the perpendicular from Q to BC is half the height, so it's half of AK. And we know the perpendicular from P to BC is half of HK. And I is the 9-point center. So we want to show that if you take the average of half of AK with half of HK, you get the perpendicular from the 9-point center to BC. That seems reasonable. How do we get the perpendicular from the 9-point center to BC? That would just be half. Okay, I see a strategy here. Okay, I think I have enough to solve this. All right. Okay, so I'm pretty sure whoever created this problem just basically used a 9-point circle. Did you guys know a lot about the 9-point circle? Complex numbers. I try to avoid that on this channel, but yeah, if you're trying to do well in competitions, complex numbers is definitely the way to go. So the 9-point circle passes through all these different points.
Isn't the perpendicular from I to BC half of AK?
If we could show that, the perpendicular from I to BC, it's half of LK, right? Because so I'm going to write this out, but the perpendicular from I to BC is half of LK. And the perpendicular from P to BC is half of HK. Yeah. Okay, so all right. So D means distance. So the distance from P to BC plus the distance from Q to BC is twice the distance from I to BC. And then we can start calculating these. So all right. And then angle LKJ is also 90 degrees. So the 9-point circle passes through, so L is the midpoint of AH. We can do the same thing. So angle LKJ is equal to 90, implies LJ is the diameter. Means the distance from I to BC is equal to half of LJ. Okay. So then we can substitute these two in. No, this is an LJ. This is LK. I'm sorry. So if we combine the above information, we get distance from Q to BC equal to twice. We'll just write it like this. 2 LK minus HK. And this is equal to, I'm going to rewrite this. Okay. Okay. So that's 2LH plus HK. And that is equal to AH plus and that's equal to half of AK. And so if the distance from Q to BC is half of AK, then Q lies on FG. All right. Does that make sense to everyone?
Yes.
All right. Yeah, and we use the fact that the 9-point circle passes through the midpoint of AH. So I didn't prove that fact, but it's not hard to show. Thanks, here, John. And yeah, your solution with complex numbers, you could post it on the Discord channel. I'm still curious to see it. All right, one sec. Let me plug in my computer. But yeah, there's a homothency about H that takes the 9-point circle to the circumcircle. So yeah, the midpoint of AH lies on the 9-point circle. All right. One second. What problem this is? Ooh, there's another cyclic quad problem from India. All right. So ABCD is a cyclic quadrilateral. I'm just trying to think. AD and BC meet at F. So, okay. All right. So E is the intersection of AC and BD. AD and BC meet at F. The midpoints of AB and CD are G and H. Let me draw on those segments. G and H. Gamma is the circumcircle of EGH. We want to show that FE is tangent to gamma. It's kind of interesting. Okay. Let's try to prove it. So that's the same as showing angle FEH is equal to angle EGH. This feels like we can use the gliding principle. I feel like I've seen a lot of these kind of problems where let me try to make it so that FEH is a little bit of a wider angle. So right now FEH is like a really narrow angle. I'm going to try to make it so FEH is like wider. That's not easy to do. But if I have something like that, We want to show FEH is equal to EGH. Yeah, if A and D are close together, then FEH is a little bit wider. Yeah, I think if A and D are close, then B and C can still be. Okay. So I kind of noticed something. So triangles DEC and ABE are similar, right? And H and G are corresponding points in those two similar triangles.
Can you repeat what you said?
Yeah, sure. So triangles ABE and DEC are similar, right?
Yes.
And also G and H are midpoints of corresponding sides in those two triangles, right?
Yes, I get it.
So yeah, so we have a lot of, so basically all the angle EGA is the same as angle EHD is basically what I'm saying, right?
Yes.
Yeah. And yeah, and not only that, also triangle FCA, I'm sorry, triangle FCD is similar to triangle FAB, right?
Yes.
And so H and G are also midpoints of corresponding segments there. Is it? Maybe it is. This might be IMO shortlist 2009. I'm not sure. But yeah, if you know the solution, don't give it away. But if you don't, yeah, feel free to share your ideas still. But yeah, we have lots of sort of similar figures here. I think you've already solved it. So yeah, don't give it away if you know the solution. Let's see. So yeah, we can kind of calculate angle FHE. It's like FHD plus DHE, and FHD is the same as FGE. Let's see.
I hope if G and H are not collinear.
You hope that what's not collinear?
F, G, and H.
That would be crazy. I doubt it. No. But basically, so I'm going to move this to the side. Kind of, I'll just type out what I'm thinking. Let me move it just a little bit more, or let me just put A right there. So not sure exactly if this will help, but maybe it will. This is kind of what I was seeing. Yeah, so if we basically this equality means that if we draw FH and we let it meet this circle at another point, so we'll call it, why not just call it I? So this but FHE is also 180 minus EHI. So that means angle EGI is equal to FGE. Okay, so that's kind of interesting. So we have an angle bisector. I don't know if that does much, but so how do we ultimately show FE is tangent? Well, we want to show, if we can show FE squared is FH times FI, that would solve the problem.
Yes.
But that's kind of the same, yeah. I feel like this might be harmonic quadrilaterals somehow. So, So if angle EGI is equal to angle FGE, then we could, let's see. You have proven angle KHE. I'm assuming, what's K? FGE. FHE is 180 minus FGE. What can be proven for the triangle GFE? Yeah. What can be proven about triangle GFE? Not sure. What can point G be for triangle GFE? What if I add so like point H for triangle GFE. Is it It's not the circumcenter. I don't think it's the orthocenter. And it doesn't look like the incenter. So I'm not sure. What is point H for triangle GFE? Yeah, it's not the circumcenter, incenter, or orthocenter. Is it the 9-point center? I'm not sure. E. FHE is 180 minus FGE. So basically, if you reflected it, it would lie on the the Humpty point. H is the G Humpty point. Okay, so because the Humpty point, it's the reflection of the midpoint of the arc. So basically, let me do this. So if we reflect H, it lies on the circle. So we want to show GH lies on the median. Okay. And I wonder if we could use projective geometry for that. So I think I see what you're saying. Let me finish up what I was thinking. Yeah, so I'm sorry, I'm going to take a slight detour from what Irajan said. So I'm just checking out something here for a sec. Oh, I'm sorry. I thought we had a harmonic quadrilateral, but now I don't think we do. So I might just go back to what Irajan said. All right. So you can prove that H is the G Humpty point if you show H lies on the median. And maybe that's possible with projective geometry. I'm not sure. Let's see. Maybe I could use like the Gauss line in some way. Ah, so we have like a, yeah, all right. So that took me a while, but so if we take the midpoint of EF, then J, H, and G are on the Gauss line of FDEC. Okay. And so basically that would mean J lies on the median from G. And then since it lies on the median, you're saying it's also the Humpty point because if you reflect it, it would lie on the circumcircle due to this angle condition. Sounds like that's what you're saying. So the Humpty point, I know it's like the perpendicular from the orthocenter to the median. I guess do you just sort of memorize that the Humpty point is the unique point? I guess I want to prove it. I just don't want to. So basically, H, it lies on the median due to the Gauss line, and when you reflect it, it lies on the circumcircle, right? Whoops, sorry. 1 sec, I'm gonna read your comment. So yeah, I'm trying to prove that H, let's see. I don't know all the theory about the Humpty point. I'm just trying to understand. So first of all, how do we know H is the Humpty point? I know it lies on the median, but the Humpty point is, it's the perpendicular from the orthocenter to the median, right? That's the definition. So how do we know H is that point? And then even if we did know that, how would that finish the problem? I'm just trying to think through it just because, yeah, I don't know as much about Humpty points. Probably I'll read up on them right after this meeting, but yeah, as of right now, I don't know a whole lot about Humpty points. Then FHXE is cyclic, where H is the orthocenter. Okay, so that's a property of the Humpty point. Yeah, I've seen that before. I've seen that property. So I proved that on my channel in like video 7-ish. Okay, so I'm going to draw the orthocenter. Is it 1? No. 2, no. 3, no. 4. There's the orthocenter. So, all right. So K is the orthocenter of EFG, and so KEHF should be cyclic. And then from there, I'm trying to see how that solves it. So FE is tangent to that circle because, let me delete this. Wait, what did I just do? Yeah, I want to delete this circle. Okay. So I get what you're saying about how the orthocenter, like K is the orthocenter, and it lies on FEH. Okay, so I guess we have an angle chase then. FEH is FDH. And then FGH. So FEH is FKH, right? Or it's H is the Humpty point since it lies on FKE. Yeah, I know. I see. I see why H is the Humpty point. I'm just trying to figure out how that finishes off the problem. So how do we go from knowing that H is the Humpty point to knowing that FE is tangent to that circle? Is that just a property? It's a property of Humpty point. Let's see. Let me see if I can prove it. Power of a point angle chase. Yeah, I think I do remember when we used this. Like in the problem that we solved before, there was something with like common tangents to two circles, but maybe it's true even if there's just a common tangent, even if there's just like a tangent to one circle. Um, hmm. Hold on just a sec. Yeah, I remember the problem you're talking about. I'm just trying to remember how we did it. So Yeah, I'm sorry. Could you write out the proof in the chat, how that power of a point and angle chase goes? I forget exactly how it goes. Power of a point and angle chase. Yeah, okay. So we showed that if FE was tangent, then E would be the Humpty point. I'm trying to remember. Yeah. I could just say refer to that prior problem. All right. I'm going to just say that for now. So I'll just write out what you mentioned, and then I guess the viewers can look more into that previous theorem. So okay. Yeah, I feel like there has to be a way using the gliding principle, but I'm just gonna write what you said for now. Okay. So I'm going to hide this circle for now, and so we can show that KEH and F is cyclic using the angle condition. Let's see. So E. So this is kind of what you're saying. And so FHKE is cyclic. And then by a property of the Humpty, so then H lies on the median of FGE. And then by properties, an empty point. See, I think it was live stream 2. I'm not 100% sure. 2 or 3. FE is tangent to gamma. All right, I'll just leave it at that for now. Let's see if we can get one more problem in. So I'm going to end it in like a half hour. But let's see if there's an easier problem that we can find that I can get done. So yeah, thanks for the help, Joni. Yeah, whoops, sorry about that. Each extra thing I can learn helps a little bit more. Let's see, I'm deciding between 2 problems. All right. There's that one. Let's see. Whoops, I didn't mean to do that. Sorry. Here we go. All right. Let's see, I'm deciding between 2 of them. All right, thanks, John. Thanks for participating. So yeah, have a good rest of your day. All right, so Ram, do you want to do the Balkan Math Olympiad or Romania team selection test? How about the Balkan Math Olympiad? So we have a circle with diameter AB. E is the intersection point of AC and BD. The circle with center B and radius BE intersects the circle at points K and L. With K is this point. L is this point. The line perpendicular to BD at E intersects CD at M, and we want to show KM is perpendicular to DL. All right. Okay. All right. Are you still there, Ram?
Yes, I just got disconnected and I rejoined.
It's all right. So yeah, this will be the last problem. We want to show KM is perpendicular to DL. So one way to show perpendicularity is we could show KD squared minus MD squared is KL squared minus ML squared. That's one way to do it. Let's see. So this is actually Balkan Math Olympiad. It should be BMO. So obviously these are both right angles, right? ADB and ACB.
Hey, you can means keep this problem for another day because there is no one. And I think when I rejoined, you were talking to yourself.
Well, it's I'll work on this for another like 20 minutes, and then if I can't figure it out, I'll just yeah, I'll just trim it off maybe. But yeah, I mean,
It will be like solving a problem yourself because I can rarely solve, and there is no one else, so you have to like solve it yourself on your own.
you helped out a lot with that first problem. I don't know if we would have solved the first problem without your idea. But yeah, no, let's see if we can get through this one. So KM is perpendicular to DL. Let's see, does that even look true from this? Just want to make sure I'm drawing everything right. No, so something I didn't draw right here. Oh, ABCD has to be at an isosceles trapezoid. Okay, that makes sense. So that kind of narrows things down a little bit. Whoops. E is the intersection point of AC and BD. Okay. And then we have points K and L. And K and L are reflections across AB. We know that. The line perpendicular to BD at E. It intersects CD at M. And we want to show that KM is perpendicular to DL. I feel like this one kind of feels like a fast one. I feel like we might be able to do it in less than 20 minutes. Let's see. So okay, so DL, KM. Yeah, they look perpendicular. Do they always meet on the diagonal like that? No. Okay. So can I show KD squared minus MD squared is KL squared minus ML squared? That's one way to do it. So is ME tangent? Yeah, ME is tangent to this circle right here because B is the center of it. So if ME is perpendicular to BE, that means ME is tangent. Okay, so ME squared is the power of it. And yeah, KL is perpendicular to AB. I wonder if that, So basically it's the same as showing angle MKL If those were perpendicular, whoops, then we'd have angle MKL is equal to angle CDL. Is that right? Something's up. Yeah, I think that's right. We want to show M, but CDL is CKL. That's the thing. I think we want to show, yeah, okay. I'm sorry, I'm just talking out loud a lot here, but if we can show KC equals KM, that would solve the problem. KC equal to KM.
For that, KL should bisect MC, right?
Yeah, KL, yeah, we want to show KL bisects MC. And the thing is, yeah, these circles, they look the same size. Let me see if I can make it so that they don't look so much the same size. It's hard to do though. Yeah, these circles are not necessarily the same size.
I wonder if KC is parallel to BD.
It could be. Let's see. No,
No.
not necessarily. Yeah. Yeah, there's got to be some kind of symmetry. Yeah, we want to show KL as the perpendicular bisector of CM, right? I wonder if we take this line ME and we let it intersect KL, and that's the same as showing that these 3 points are collinear, F, C, and B. Yeah, can we show that F, C, and B are collinear? It feels like the radical axis theorem, doesn't it?
No, I think this is not not a problem. Like you can use a radical axis theorem to solve. There is much simpler way if you can try.
I think that the radical axis theorem is a simple theorem, right?
Yes.
Yeah, wait a second. What if we take the circumcircle of ECB? I think that might do it. So if we draw the circumcircle of ECB, so that's a right triangle, it also passes through O, and then I think the radical axis theorem solves the problem. Yeah.
Yes.
Okay. Let me think about that. Yeah. Okay. So yeah, I'm just going to write that up. But that pretty much solves the problem. Okay. Yeah, I guess the text might overlap the diagram, but all right, let me delete the stuff that I added. Okay, so the only thing I really added was point F, right? And then I added in that circle.
Yes.
Okay. So all right. And then FE is perpendicular to that circle. And then we can apply the radical axis theorem. EC and KL are concurrent. Okay. And then from there, we should be able to prove KMC is isosceles. We could prove that FMC is isosceles.
I think you didn't need to put radical axis theorem because angle FEB is already 90 and angle ECB is also 90. So if you could have noticed some like 5 to 10 minutes, then you can see that.
But you want to show that KL passes through, like FEB is 90 degrees, and what was the other one you were saying?
ECB.
ECB and FEB. I agree those are both 90 degrees. But how does that, like, I still think you need that KL passes through that point, right?
Yes, you're right.
And so Okay, so that should be enough to show. Can we show FMC as isosceles? That should be an angle chase because, yeah, let me draw the circle ECB. And then we have angle DCE. Hold on one second. Oh yeah, okay, so I'm just thinking through this. How do we show F?
Yes, because angle, if you can see that angle FCD equals angle FCD equals angle DAB, and angle FMC is angle MEC plus angle uh, ECM, because angle ECM is ABD and angle MEC is EBC. So, and also this is a isosceles trapezoid, so they must be equal.
So I think I have another way of seeing it. I'm just going to type, sorry. I'm sure this is not the only way, but all right. So and then once we have that, how did I do that? KM. Okay, so then angle MKL. Angle CKL. CDL. So CD is perpendicular to KL, implies MK is perpendicular to DL. All right, and that should do it. All right, so I guess we'll stop here. So for everyone who participated and is viewing this on YouTube, thanks for watching. And if any of you want to join again, feel free to email me. Thanks, everyone.